Welcome. In this video, we will cover Part 2 of Chapter 9, the chemistry of alkynes. The next reaction we'll look at is the reduction of alkynes. This reaction is analogous to the reduction of alkenes. We can convert an alkyne to an alkane using two equivalents of hydrogen gas and platinum. The first addition will produce the cis-alkene via syn addition, and then a second equivalent of hydrogen will reduce the alkene down to the alkane. In order to convert an alkyne to an alkene, we will need a catalyst that will stop the reaction at the alkene and not be able to reduce all the way down to the alkane. Such reagent exists, and it's called Lindlar's catalyst. Lindlar's catalyst is able to convert the alkyne to the cis-alkene. The way this reaction works is that the catalyst is able to reduce the activation energy needed for the first reduction, but it does not reduce the activation energy needed for the second reduction. This means that we can obtain the cis-alkene product. If we would like to obtain the trans-alkene, we can use dissolving metal reduction. This will reduce an alkyne to the trans-alkene, and it uses sodium metal and ammonia. This reaction can be considered stereoselective for the anti-addition of the two hydrogens. A proposed mechanism for this reaction is shown. The reaction involves single electron chemistry for the first stage. A single electron from sodium is transferred from the alkyne, creating a radical anion intermediate on the alkyne. This can then be protonated, followed by nucleophilic attack of a second radical single electron to produce another anion, which is then protonated with a molecule of ammonia. The sodium atom transfers an electron to the alkyne, forming a radical cation intermediate. When we go to show a single electron arrow, it's important that we use the arrows with just one barb. This arrow indicates single electron movement. The reason that we obtain the trans intermediate in this step is because of the relative energies of the two conformations of this radical anion. In the trans intermediate, these electrons will not repulse energy due to steric interactions. In the second step of the mechanism, a proton transfer occurs, followed by the nucleophilic attack. Then the product is finally formed with the protonation. Here is a summary of the three reactions we've learned to reduce alkynes. First, we can reduce an alkyne all the way to the alkane using hydrogen and platinum. This reaction would be considered unselective, as it would go all the way to the alkane. We are not able to obtain either of the alkene products in this fashion. If we'd like to obtain the cis-alkene product, we can use hydrogen and Lindlar's catalyst to stop at the cis-alkene. If we would like to obtain the trans-alkene, we can use ammonia and sodium metal. In Chapter 8, we learned about the addition to alkenes. In this reaction, we can break the pi bond of an alkene and add two substituents to either side of the alkene. In Chapter 9, we're going to learn about the analogous reaction to alkynes. In this case, we can break the pi bond of an alkyne and add two substituents to either side. At the end of this reaction, we obtain an alkene product. In some cases, we can do multiple addition reactions in a row. For example, if we do a hydrohalogenation reaction, we can add a halogen to one side and the hydrogen to the other side of the alkene. If we use excess of the HX reagent, then we'll obtain the geminal dihalide product. If this mechanism was analogous to the hydrohalogenation of alkynes, it would require the formation of the vinylic carbocation. Vinylic carbocations are extremely unstable, so this mechanism is unlikely to occur. Kinetic data suggests that the rate of this is a first-order reaction with respect to the alkyne, and second order with respect to HX. This mechanism must be consistent with a term molecular process. In this mechanism, we use two molecules of the hydrohalogenation reagent. The first molecule acts as a nucleophile, and the second molecule acts as an electrophile. In this transition state, we obtain two new bonds forming with the alkene at the same time. It is possible that there are several competing mechanisms occurring, but this is our best estimate as the mechanism of this reaction. If we use the hydrohalogenation with peroxide as one of the reagents, we're able to obtain the anti-Markovnikov addition just like we're able to obtain with alkenes. This reaction will only work with HBr, and we'll cover the radical mechanism which this reaction undergoes in Chapter 10. The hydrohalogenation of alkynes and the elimination of dihalides represent complementary reactions to transition between an alkyne and a dihalide. This is analogous to looking at the forward reaction and reverse reaction of addition reactions of alkenes to form alkanes and the elimination of alkanes to form alkenes. In Chapter 8, we covered the hydration reaction of alkenes to form alcohols. Alkynes can also undergo a acid-catalyzed Markovnikov hydration reaction. In this case, they form an enol. The enol is an alcohol directly attached to an alkene. The enol is in equilibrium with its ketone form and will rapidly convert to the ketone. We can look at the mechanism of this reaction in more detail. First, the alkyne attacks the mercury to form this intermediate, which can then undergo nucleophilic attack by water. The water is deprotonated, which then forms the enol. Once the enol is formed, a proton can replace the mercury to form an enol intermediate, which can then undergo the tautomerization process. The keto-enol tautomerization is where an enol is converted into a ketone and involves two proton transfers. The first proton transfer removes a beta proton to the oxygen to form a resonance-stabilized carbocation intermediate. The resonance form, which has a positive charge on the oxygen, can then be deprotonated to form the ketone. The enol and ketone forms are tautomers of each other, and the equilibrium is generally going to favor the ketone. Hydroboration-oxidation is a reaction where we learned to convert an alkene into the anti-Markovnikov addition product. This reaction can also occur with alkynes. It will also be regioselective for the anti-Markovnikov addition, and will also produce an enol intermediate that can tautomerize to an aldehyde. In this case, the tautomerization will be a base-catalyzed tautomerization. The base will remove a proton from the oxygen, and then the enolate anion that is formed has a resonance structure which will put a negative charge on the beta carbon. The beta carbon can then deprotonate a molecule of water to form the aldehyde. If BH3 is used in the hydroboration oxidation, then the alkyne can undergo two successful additions. In order to prevent this, a bulky borane such as 9-BBN can be used to prevent this second addition. A modified borane reagent can be used to convert the alkyne to the corresponding aldehyde. In summary, for controlling the regioselectivity of hydration of a terminal alkyne, the Markovnikov hydration will yield a ketone at the more substituted position of the alkyne, and the anti-Markovnikov will yield an aldehyde at the less substituted position of the alkyne. The halogenation reaction of alkynes is also analogous to that of alkenes. In this case, we will yield a tetrahalide. Two atoms of halogen will be added for each pi bond that is found in the starting material. Using excess halogen with carbon tetrachloride as a solvent, we're able to add 4 halogens to the molecule and remove 2 pi bonds. When one equivalent of halogen is added, we obtain both the anti and the syn addition products. The major product will be the anti-halogenation product. And the mechanism for the alkyne halogenation is not fully understood, but if it was the same as halogenation to an alkene, we would only observe the anti-product, which is not what the experimental data indicates. Ozonolysis for an alkyne is similar to an alkene. For every carbon-carbon bond that's found in the starting material, we will obtain a carbon-oxygen bond in the product. This means that for an alkyne, we will obtain a carboxylic acid. In the case of a terminal alkyne, we will obtain a carboxylic acid and carbon dioxide as our other product. Earlier, we discussed that a terminal alkyne can be converted to the alkynide ion using sodium amide. This alkynide ion is a source of nucleophilic carbon, and the alkynide ion can act as a nucleophile in an SN2 reaction. This means that we can form a new carbon-carbon bond, as we have already looked at several different electrophilic versions of carbon. Up until this point, this is the first reaction that we've learned which allows us to produce a carbon-carbon bond and take 2 different sized carbons and piece them together. We have looked at using cyanide as a carbon nucleophile, but that will only extend the carbon chain by 1 carbon. Utilizing this reaction, we can create much larger molecules from smaller molecules. This alkylation is an SN2 substitution reaction, so it'll work best with methyl and primary halides as our electrophile. Here's an example of the reaction. We can take our acetylene and deprotonate it to form the ion in the terminal position. Then the SN2 reaction with ethyl iodide will add a new carbon-carbon bond and expand our carbon chain length by 2. Acetylene can undergo 2 successful alkylations because we have 2 terminal alkyne protons. So if we use sodium amide and 1 alkyl halide, we can add the first R group, and then we can use a second alkyl halide to add a second R group. We can even do a double alkylation that includes 2 different R groups. For example, if we start with 1 equivalent of sodium amide and then use ethyl iodide, we can add an ethyl group. Then we add the second equivalent of sodium amide and methyl iodide to add a methyl group. Using this reaction, we can obtain complex target molecules by building the carbon skeleton 1 bond at a time. Every time we learn a new set of reactions, we want to incorporate these into our synthesis toolbox. In this chapter, we've learned how to convert an alkyne into an alkene and then into an alkane, and we can use halogenation reaction followed by elimination reactions to convert an alkene into an alkyne. We can use hydrogen and platinum to convert the alkene to the alkane, and in chapter 10 we'll learn the missing link, which is how to convert an alkane up to an alkene.